So this we have calculated this A matrix, okay, 0, 1, minus 1 by 3, minus 2 by 3 from the values of m is equal to 3, c is equal to 2 and k is equal to 1. Okay. Now what we'll do is we will find the eigenvalues of A matrix. Okay. For that, yeah, what I'll do is just clear this. So A matrix is equal to 0, 1, minus 1 by 3, minus 2 by 3. So 0, 1, minus 1 by 3, minus 2 by 3. Okay. So this is the A matrix. Now if I find the eigenvalues of this, it is giving these roots. So this is the same root as what we saw previously, right? So here if you see the roots here, minus 0.33 plus 0.47i and minus 0.33 and minus 0.47i. So that's the same thing you're getting here in MATLAB. Okay, so what it means is the poles of the transfer function is nothing but eigenvalues of A. Okay, so the poles are nothing but the eigenvalues of the matrix A. So how do you make a system stable? How do you know whether the system is stable? How do you know if the system is stable? You have the S-plane. Okay, so suppose you have a pole here and a pole here. Is this stable system?
No, sir.
It's not. Okay, so what you do is you use a method called as pole placement. Pole placement, and shift this pole over to the left side. Okay, so pole placement is a method of uh, control. Okay, it's a method of control where you shift the poles from the undesired position to the desired positions. Okay, you shift the poles from the undesired position to the desired position. That is called as pole placement method. Since poles are nothing but eigenvalues of A. Okay, eigenvalues of A is nothing but poles. Okay, so now if I have to do pole placement, then I have to change this A matrix. Okay, I have to change this A matrix. If I modify A matrix, then I'll get the desired poles. So now the desired poles, if I have to get desired poles, means the stable poles. Okay, desired poles, if I have to get, I have to modify A matrix. Modify A matrix such that the eigenvalues will change and you'll get the desired poles. So to do this, what you do is you use a formula. CL means closed loop. Okay, ACL. Okay, so this is closed loop is equal to, this is the formula, A minus BK. Okay, so this is the modified, that is closed loop. Okay, modify means what? You take the feedback and modify, correct? Okay, so this is the closed loop of the A matrix, which is A minus BK. Okay, so what is B here in this case? In this case, what is B? There is AX plus BU.
BU, sir.
Okay,
Yes, sir.
0 1 by m. Okay, so suppose that is B. Okay, and what is K will I'll tell you. So suppose you have um, suppose you have A matrix is equal to, I am changing the A matrix now. Suppose A matrix is 0 1 2 minus 1. Okay, this is the A matrix 0 1 2 minus 1. Now we'll just quickly go to MATLAB and give this matrix. A is equal to 0 1 2 minus 1. Okay, so this is the matrix. Now the eigenvalues of this is 1 and minus 2. So is the system stable?
No, sir. We still have a positive pole.
Positive 1 is there. Okay, so what is the desired one? Desired one is say minus 1, sorry, actual is actual what we are getting is 1 and minus 2. Okay, by using a pole placement method, I want the desired poles to be at say minus 1 and minus 2. Okay, this is the actual one. Okay, so this is the desired one, minus 1 and minus 2, so that the system becomes stable. Now what I do is I use this formula. Okay, so A is nothing but 0 1 2 minus 1. Okay, minus B. Okay, B is given as, in this problem it is say 1 and 0. Okay, I'm just defining B. Okay, so A is equal to this, B is equal to this, so B is 1 and 0. So what is this K matrix? K matrix consists of K1 and K2. Okay, K1 and K2. So you need to find this. What will be the value of this? This will be, if you multiply this, what will
K1, sir.
this will be?
K1.
Only K1?
Yes, sir. Because it's 0.
This will be K1 and K2, no? It is nothing but multiplying by 1.
Yes, sir.
Okay, so this will be 0 1 2 minus 1. This 1 and 0 is like 1 only.
Okay, sir. Okay, sir.
Okay, so this will be equal to A minus BK. Okay, so if I subtract this, what will I get? I'll get minus K 1 1 minus K2 2 minus no 2 only, and then minus 1. Okay, so this is A minus BK equal to minus K1 1 minus K2 2 and minus 1. Okay, there is no second row here. Okay, so minus K1 1 minus K2 2 and minus 1. So this is the A minus BK matrix. Now you have to know what should be the K1 and K2 value, so that this we get the desired poles. So how to do that? So we know that the how do you find eigenvalues? You find the determinant of A minus lambda I equal to 0. So this is the characteristic equation to determine the eigenvalues. Okay, so where lambda is the roots, that is eigenvalues. Okay, so this is the one. Now A modified means what? It is A minus BK minus lambda I determinant. Okay, if you find out, then you'll get the modified eigenvalues. Okay, so for that, what you do is you have this A minus BK, that is modified matrix, minus K1 1 minus K2 2 and minus 1. So if you put it in this form, it will be minus k minus lambda, okay, 1 minus k2, 2 and minus 1 minus lambda. Take the determinant of this. What will be the determinant of this? What I've done is I've just written this a minus bk, this thing, minus lambda I. Okay, so this is what is done. Any doubts here?
No, sir.
Okay, so find the determinant of this. So it is, sorry, there must be k1 here. Okay, so this is minus k1 minus lambda multiplied by 1 minus lambda minus 2 into 1 minus k2 equal to 0. Okay, so what will be this one? If you multiply this, I'll just write the equation. You will get it as lambda square plus 1 plus k into lambda plus k1 plus 2k2 minus 2 equal to 0. If you multiply this, you will get this. Okay, so it is lambda square plus 1 plus k lambda plus k1 plus 2k2 minus 2 equal to 0. Now, what is the desired poles? Desired poles are minus 1 and minus 2. So what should be this equation? It must be lambda plus 1 multiplied by lambda plus 2 equal to 0. Correct? So this is lambda equal to minus 1 and lambda equal to minus 2. Eigenvalues are nothing but the poles, no, of this matrix. So this is the desired one. Are you able to understand?
Yes, sir.
Okay, lambda equal to minus 1, lambda equal to minus 2 is the poles. So this is what is desired one. Now if you compare this, so this, if you multiply, what do you get? Lambda square plus 3 lambda plus 2 equal to 0. Okay, so this is the desired one. Desired. Okay, this is desired. Now if you compare this equation with this, then what you get is 1 plus k must be equal to 3. 1 plus k, this is not just k, this is k1. Okay, 1 plus k1 is equal to 3 just by comparing. Okay, and then 2k2, sorry, it's not, it is k1 plus 2k2 minus 2 is equal to what? 2. Okay, so what is k1 equal to? K1 is 3 minus 1. Okay, 2. So substitute this 2 here. What will you get? K2 equal to? K2 will be
1, sir.
K2 will be equal to 1. Okay. So now K1 equal to 2 and K2 equal to 1. So you just see here, we have defined what is A matrix. We'll define B matrix also. What is B matrix? 1 and 0. Okay. This is B matrix. What is K matrix? We got the values as 2 and 1. Okay. 2, 1. Okay. So this is K matrix. Sorry, the brackets are wrong. 2 and 1. Okay, so this is a K matrix. Now you need to find what is A minus B K. Okay, so A minus B K, this is, you need to put a star there. So this will be minus 2, 0, 2 and minus 1. So this is modified or the closed loop A matrix. This is the closed loop A matrix. Okay, A minus Bk is the closed loop A matrix. Now if you find the eigenvalue of this one, what you should get? You get minus 1 and minus 2. So this is the desired poles, right?
Yes, sir.
So what we have done here is we have used the concept of pole placement. Previously there was a pole at 1 and minus 2. Okay, so the pole was at 1 and then at minus 2. So since the system is unstable, we wanted to shift this pole to the left side. So the desired pole is minus 1 and minus 2. Okay, so the closed loop A matrix is given by A minus Bk. Okay, when you take this A minus Bk given A and B, you get this. Okay, once you get this, what you have to do is, this is modified. Modified, when I write, it is A minus Bk. Okay, A minus Bk minus lambda I, the determinant must be equal to 0. This is from the mathematics for the eigenvalues. So this will be equal to, we have got the modified A. Okay, so you got that as minus k1, 1 minus k2, 2 and minus 1. So what you do is you just take the A modified minus lambda I. Okay, the determinant must be equal to 0. So equate it to 0 and you'll get this equation. Now you know that the desired poles are minus 1 and minus 2. So you write it as lambda plus 1 and into lambda plus 2 equal to 0. So the roots are minus 1 and minus 2. Okay. So you multiply this equation, you get lambda square plus 3 lambda plus 2 equal to 0. So this is the desired equation. Now you compare this equation with this one. Okay, this is the lambda term. So 1 plus k1 must be equal to 3. Okay, so this doesn't have any lambda term. So 2k plus k1 plus 2k2 minus 2 equal to 2. Okay, so you get k1 and k2. Now what you have to do is you have to take this. Okay, it is a minus bk. So a minus bk is what you need to do now. So this is what you need to do. Okay, so you have done that and you have got this k1 and k2. Now put this, substitute this for this a minus bk. You know what is the value of k now. So substitute this A matrix minus B multiplied by K. Okay, so that is what I did in the MATLAB. Okay, so A minus BK is what we did and this is what we got. Now this is the modified or the closed loop A matrix. Okay, this is a closed loop A matrix. So when you take the eigenvalues of this matrix, you must get it as the desired poles. The eigenvalues of that matrix must be the desired poles of that matrix. Okay, so this is how you control a system by using the concept of pole placement. Okay, so just that you should know this. This is A minus BK is the closed loop of A, and poles are nothing but the eigenvalues of this A matrix. Okay, so looks a bit complicated, but I think I've revised it also. So I think you should be able to understand a bit at least. What is the confidence level in these things? How is the understanding of this concept?
Kind of understood, sir. We'll watch again and then we'll understand it.
Okay. So yeah, it's not as easy as the transfer function. Okay, but state space model has advantages of multiple input and multiple outputs. Okay, so that's the advantage you get when you learn state space models. compared to transfer functions. So, and that's the reason why we are doing this. So we'll not be going into too much depth of these things, but I've just covered the basics of this, what is the pole placement method and how it works. Okay, so we'll do this in the Simulink sometime and try to understand how it works. Instead of transfer function block, we can use a state space model block and try to do that. Okay, so any questions, any doubts here? So for your quiz, you will have I'll list out the topics in the Google Classroom. Okay, I'll list out the topics in the Google Classroom today. You can make a note of that. So for the quiz, we'll give you the portions for today. We'll give you the portions today for the quiz. Okay, so prepare well for the quiz also. And any doubts in these topics, let me know. In the fifth module, it's actually the PID and all you'll be comfortably doing, I think. You know the role of P, I, and D, right? So I have discussed, I have taken too many classes on that PID controller, so you must be able to do it. The second part of that module is this one, the state space model. So make sure you understand these things so that you are able to solve some of the numericals. Okay, pole placement method is important to understand. Any questions? Any questions?
No, sir.
No, sir, no question.
Okay, we'll stop it here. Thank you.